Today we're going to start the lecture number 3 from chapter number 3. And the learning goals for today are to introduce uniform and non-uniform circular motion, and to calculate the magnitude and direction of the acceleration in a circular motion. So these will be the goals for today's lecture. Now, we'll look at motion in a circle. Okay. So when you go, or when an object, a car, a particle, whatever it is, moves along a curved path, the velocity changes. Okay. And we discussed that in the first lecture, when we said when you go around the curved path, you can change two aspects of your velocity. You can change the magnitude of your velocity, which is the speed, and you can also change the direction of your velocity. And we talked about two accelerations. We talked about A parallel, and we said this is along the direction of the velocity, and in this case you're moving tangent to the curved path. And we said that your tangential acceleration here is responsible for changing the speed of the car, which is the magnitude of your velocity. But since you're going around the curved path, that means you have to change your direction. And since your velocity is always tangent to the curve, that means when it gets to a point, let's say here, that's how your velocity is going to be. So you're changing direction. And you need acceleration to do that for you. And we talked about the perpendicular component of the acceleration. And we said this will be pointing toward the center of the curvature. And we said this is responsible for changing your direction. And of course, this will be your net acceleration here. So your net acceleration will be written as A parallel plus A perpendicular in vector form. You don't adding, you're adding them as vectors. And we said that if your parallel acceleration is in the same direction as your velocity, in that case we said you are speeding up. But if your parallel acceleration is anti-parallel or opposite to the direction of your velocity, and of course you still need the A perpendicular that points toward the center to change your direction of your velocity. Now your net acceleration will be pointing in this direction, and in that case we said you are slowing down. So while you're speeding up or while you are speeding down, the perpendicular component of your acceleration always points toward the center of the curvature, and it is responsible for changing the direction of your velocity. But the A parallel is the one which could be along the direction of your velocity or opposite to it, and that's responsible for changing your speed or the magnitude of your velocity. And in these two cases here, we're talking about when you're speeding up and when you are slowing down. Is this clear? Any question on this? So we dealt with this in previous lecture. Today we're going to talk about circular motion. And we are going to start with uniform circular motion. Now, as we stated in the previous slide, when you go around the curved path, you need a parallel component of the acceleration to change the magnitude of your velocity, which is the speed, and a perpendicular component of your velocity that it's going to change the direction of your velocity. And that's how you can go around the curved path or a circle. And we said that your acceleration can be written as a parallel plus a perpendicular in vector form. Now, what happens if you can go around a circle with a constant speed? That means the A parallel, it's going to equal to 0 because you're not changing the magnitude of your velocity. So you're only left with the perpendicular component of your acceleration. So this will go to 0, and your acceleration here will equal to the A perpendicular, and the A perpendicular is always pointing toward the center, and that's why your net acceleration here will be pointing toward the center of the circle. So when we talk about uniform circular motion, we talk about motion with constant speed. And if you have constant speed, then the parallel component of your acceleration is 0, and you only have the perpendicular component of your acceleration, and that points toward the center. You will find out that the angle between your velocity and your acceleration is 90 degrees. So the acceleration and the velocity are perpendicular to each other when you have uniform circular motion. And I told you in previous lectures, it is wrong to say that you can go around a circle with constant velocity, because velocity is a vector, and the vector has a magnitude and direction. And if you want to go around the circle, you have to change your direction. You cannot maintain constant velocity. But you can go around the circle with constant speed. And this is what we mean by uniform circular motion. So in uniform circular motion, you're going around the circle with constant speed, but not constant velocity, because you need to change the direction of your velocity. And to do that, you need acceleration. And the acceleration will be the perpendicular acceleration that we talked about, which is responsible for changing your direction. And this velocity is always going to be pointing toward the center of the circle. And we call it centripetal, meaning something that basically points toward the center. So this is what we have here. When you basically move around a circle, you need a centripetal acceleration, which is responsible for changing the direction of your velocity. And when you move in a circle, your velocity is always tangent to the circle. And the centripetal acceleration is always pointing toward the center, and that's why the angle between both of them is 90 degrees. So how can we calculate this centripetal acceleration? What is the magnitude of this centripetal acceleration? Now, we want to calculate an acceleration. So you know that two things that we did previously, that average acceleration is equal to delta V over delta T. And A should be in the limit as delta V by delta T in the limit as delta T goes to 0. And that will give you dV by dt. We know these two. So now, if you are at position P1, here, now you will have a velocity V1 which is tangent to the circle. And at position 2, and here we're talking about uniform circular motion. And uniform circular motion, that means constant speed. So you have V2 here. If you look at the length of the vector V2 and the length of vector V1, they are the same length, meaning they have the same magnitude, meaning it's the same speed, but they have different directions, and they always have to be tangent to the circular path. And what is causing this change in direction is the centripetal acceleration. Now, if you look at the origin of the circle, and you're moving around the circle will have a radius r. So at position 1, you are r away from the center of the circle, and at position 2, you are away from the center of the circle. Now, I can basically connect position 1 and position 2 here, as you can see in the diagram, and I say this is to me equals delta S. And this is what we have in this triangle here. You have a triangle here where the sides of this triangle is R and R, and the base here, which basically separating the two, it is delta S. Now, I can come exactly in the middle and drop a line which makes an angle 90 degrees with the base, and that will cut my base into delta S by 2. And of course, that will cut the angle. If we call this angle here delta phi, you're moving through the angle delta phi, it will cut this angle delta phi over 2. So you have a right angle triangle here where your hypotenuse will be r, and your opposite to delta phi over 2, it will be delta S over 2. So if I take sine delta phi over 2, it will equal to delta S over 2 divided by r. And that's basically what you get from this triangle here. Now, I can do the same thing with V1 and V2. I can take the difference between both of them. And that's what we're doing here. We're connecting, taking tail to tail. And that will give me delta V here. Now, if you're moving through an angle delta phi to move from position 1 to position 2, it is the same angle between V1 and V2. So when you do that, you also have a triangle here, where if you cut it midway, you will have a delta phi by 2. And this one here, when you cut it, it will be delta V by 2. So again, if you take sine delta phi by 2, it will give you delta V by 2, which is the opposite to the angle, divided by the hypotenuse. And the hypotenuse here is V1 and V2 are the same. They have the same magnitude. And you can see that I'm not putting a vector on top of them. I'm just looking at magnitudes here. Okay. So what I'm saying here, that sine delta phi over 2 will equal to delta V over 2 over V1 or V2, or I can just say V. Okay. Now, if you look at this result here and this result here, both of them, they have sine delta phi over 2, sine delta phi over 2, meaning delta S over 2 over R will equal to delta V over 2 over V1. The 2 can drop out. And what you have here, you have delta V over V1 will equal to delta S over R. So this triangle here and this triangle here, I can basically relate them as delta V over V equal to delta S over R. Is this clear? Any question on this point here? Is this clear? Okay, on this point. Now it comes in calculating my acceleration. And my acceleration, the average is equal to delta V over delta T. So I need to calculate delta V. Now we say here that delta V, and you have an absolute value around that. An absolute value here, that means I'm taking the magnitude. If you look at what I did here, I did not put an arrow on the top. I'm just taking the delta V. But I'm putting the absolute value here just to tell you that I'm taking the magnitude of delta V, which over V1 will equal to delta S over R1, which is this result here. So from this equation here, delta V, or the magnitude of delta V, will equal to V1 over R delta S. Now, if I follow the definition of my average velocity, and the average velocity should equal to delta V over delta T. Now, if I take the magnitude of my average acceleration here, well, AF, and you can see I don't have an arrow on the top. That means I'm just taking the magnitude. It will be the delta V as a vector. I put an absolute value around that. And delta T here, it's a scalar quantity. Okay. And T2 is going to be greater than T1. Okay. So it's a positive value. Now, delta V here, as we obtained from the first equation, it's equal to V1 delta S over R. but I have to divide by the delta t. So I have v1 over r delta s over delta t. This is now my average acceleration. Now, if I want to get my instantaneous acceleration, I will have to take it in the limit as delta t goes to 0 of v1 over r1, meaning that's my speed. v1 is the magnitude, which is the speed, and r is the radius of my circle, which is also a magnitude, delta s over delta t. But when you take it in the limit as delta t goes to 0, then you're going to get ds by dt. And that's what we do when we take the limit. It will be dv by dt. But in this case, I have delta s over delta t, which will become ds by dt. And ds by dt along this circle, it will equal to v, or v1, which is the speed. So now you have v times v over r, and that will give you v squared over r. So the instantaneous acceleration in this case, and remember, we said that it's a uniform circular motion. That means my speed is the same, and I went through this argument to show you how we can relate these two triangles, and I will get my acceleration now, or the magnitude of it. It's equal to v squared over r. I want you to pay attention. There is no vector sign above a, meaning that I am looking at the magnitude of this. Now, we put a subscript here which called rad, and rad here means radial, which is along the radius. So when you go around a circle and it has a center, your acceleration is always going to be pointing toward the center of the circle. So for example, if the object is here, the acceleration will be pointing this way. If the object is here, the acceleration will be pointing that way. If the object is here, the acceleration will be pointing this way. If the object is here, the acceleration will be pointing that way. It always points toward the center. And it has a magnitude equal to v squared over r, and that's why we called it a rad, or radial, which is pointing toward the center, or the other word that we use for it is what we call centripetal acceleration. So you may hear radial acceleration, you may hear centripetal acceleration. Okay, centripetal meaning center seeking. That means the one that goes toward the center, and that will be the magnitude of your instantaneous acceleration. Is this point clear? So a radial or a centripetal is equal to v squared over r. Now, if you are moving with a constant speed around a circle, well, your motion is going to be periodic. For example, if we take the case of the Earth orbiting the Sun, the orbit is not circular, but it's nearly circular. We have a period, okay, which goes around a period of 1 year. Okay. That's, the Earth is not entirely going around a circle, near a circle, but I'm trying to say if it's a perfect circle, then when you go around at constant speed, you will finish the circle in a time which we call it the period, and we will give it a symbol T capital here to mean what? To mean the period. Now, you're all familiar, if you are moving with constant speed, you don't have any accelerations, so your speed is going to be equal in the distance divided by the time. So you see, I'm using a symbol V here. I'm not putting an arrow on top of it. That means magnitude. That means that's speed in this case. Now, in the case of a circle, when you complete one full circle, you're going to look at the circumference, and the circumference of the circle is 2 by r. And the time to complete one period, we'll use the symbol T here, capital T here, meaning that you're completing one period. So if I want to obtain this period here, it will be the circumference of the circle, which is 2 by r divided by v. It's similarly what we're putting here. Remember, we used delta S to indicate part of our circle, but when you go around a full circle, this will equal to 2 by r, and this is basically will give you your period. Again, I want to tell you that the V here, you do not see an arrow on the top. I'm not talking about velocity here, I'm talking about speed. And you know that time is a scalar quantity. So I'm just looking at a magnitude. So that's basically the period to go around a circle. And if you know the period, you can also calculate the speed. And the speed will equal to 2 pi r over t. And that will give you your speed. And we already talked about a rad equal to v squared over r. And your v squared, v here is equal to 2 by r over t. So if you want to do that, you'll put your v squared. V squared will give you 4 pi squared r squared over t squared, but you still have the r here, which is this r here, and this should be squared, and this should be r here, but this will cancel the square, and that's why here you will have, in this case, your radial acceleration will equal to 4 pi squared over t squared. So when you are performing uniform circular motion, your speed is constant. That means you're going to have a regular period in completing the circular motion. And you need to change the direction of your velocity, and you need acceleration, which is equal to v squared over r. And also, a rad can also equal to 4 pi squared r over t squared. So you can basically obtain your radial acceleration if you know the radius and either the speed or the period. And you can use either of these formulas to decide on your radial acceleration. Any questions so far? So that's the idea when you go around a circular motion, or what we call uniform circular motion. When you go around a circle, you can go with constant speed, which we call uniform, but you cannot do it with constant velocity because you're going to change the direction. And in changing the direction, you need acceleration that pulls toward the center. And this is what we call the centripetal acceleration, which is equal to v squared over r, or 4 pi squared r over t squared. Let's take an example here. And the example that we have here, if the maximum centripetal acceleration of a car moving on a flat horizontal curved path without skidding is 9.4 meters per second squared. If the car is traveling at a constant speed of 40 meters per second, what is the radius of the tightest curve it can negotiate? So they give you the centripetal acceleration and they tell you this is the maximum, okay? And in chapter number 5, we'll talk about forces and probably we'll talk about the effects of that. Now they want the radius and the smallest radius that we can get with this. Now, you know that your speed is constant in uniform circular motion. They give you the ARAD, which is equal to 9.4 meters per second squared. And they give you your speed, which is 40 meters per second. And they want the radius. So you know that A is equal to V squared over R. So your R will equal to V squared over A, which is 40 squared over 9.4. And it will give you 170.2 meters. By the way, I can ask another question here, and I say the period, the time required to complete this. Okay. And you know that A is equal to 4 squared by 4 by squared R over T squared, and in that equation, you know everything except for the T, and you can also figure out the period. Now we added here just to show you 40 meters per second is 144 kilometers per hour. So that's not advisable to go around, let's say, a small circle with this speed. Okay. Another example here. Passengers or a carnival ride move at a constant speed in horizontal circle of radius 5 meters, making a complete circle in 4 seconds. What is their acceleration? If you look at the example carefully, they tell you they move in a horizontal circle, so it's a circular motion, and they tell you constant speed, you know right away it's uniform circular motion. They give you the radius here, and they give you the T. Okay. And they ask for the acceleration. Now, you know that A is equal to ARAD, which is V squared over R. And we already talked about what V is, and we said that V should equal to 2 by R over T. So you can basically figure out your speed. And if you put in the speed, which is V squared over R, you will get 12.2 meters per second squared. And that's basically your radial acceleration here. And it's pointing toward the center. You can do it also in one step where we said that A rad is equal to 4 by squared R over T squared. And you already know. You have the T, you have the R, and you will get the same answer. Is this clear? Now, another example here. An aeroplane makes a gradual 90-degree turn while flying at a constant speed of 200 meters per second. The process takes 20 seconds to complete. For this turn, find the magnitude of the average velocity of the plane. So they tell you that it is a constant speed. And it makes a turn, a gradual turn. A gradual, that means it's not sharp. If it's something like this, that's not a gradual. That's not what they're talking about. Okay? They're talking about a gradual. That means it will go something like this. What you see, it's like a curve. And this will be of a radius r. Okay? You know that this is your initial velocity v1. That will be the v2. The speed is the same, but the direction is different. And that's why if you look here, we say v1 is equal to v2 is equal to 200 meters per second. We have no arrows here on v1 and v2. We're only talking about speeds here. Now, average velocity, it's equal to v2 minus v1 over t2 minus t1. The time is 0 to 20. Now, I can get delta v. You can use the argument that we did when we looked at triangles, but you can also say, you can basically make an x-axis, x and y, since it is this way. And you can say that the v1 is 200 I hat, it's only along the x direction. And the v2 is equal to 200 j hat. Notice that we're putting arrows on the v. Now we're talking about velocity. Now delta v will equal to v2 minus v1 over t2 minus t1, which is 200 j hat minus 200 I hat over 20 minus 0, which will basically give you your average acceleration here will equal to 10 j hat minus 10 I hat meters per second squared. They ask you about magnitude. So the magnitude here is the absolute value, square root, and we take the positive because always magnitude you take the, whenever you do a square root is plus or minus, but when you're talking about magnitude, it's always positive. So it is the square root of 10 squared plus 10 squared plus minus 10 squared, which is square root of 200, and it gives you 14.1 meters per second squared. This is basically uniform circular motion when you go around with constant speed. Now, you can go around the circle and you can change both. You can change your the speed, and you can also change direction, because when you go around the circle, you're going to change the direction of your velocity. So in this case, we call it what? We call it non-uniform circular motion. Non-uniform circular motion here, that the speed is going to vary. By the way, the velocity is going to vary either in uniform circular motion or non-uniform circular motion, because you're going to change the direction. But it is the magnitude of that velocity, which is the speed. In the uniform circular motion, the speed is constant. In the non-uniform circular motion, your speed varies. And if you recall in the early slides, when we talked about circular motion and we talked about acceleration, and we said the acceleration has a parallel plus a perpendicular, okay, where the a parallel basically responsible for changing your magnitude of the velocity, which is the speed, and this one is responsible for changing your direction. In a circular motion, this A perpendicular, we call it the magnitude of it, we call it A rad, which is equal to V squared over R. And this is the component that is basically responsible for changing the direction of your velocity. And if you notice here, that's A rad, that's the A rad here, A rad, A rad. It's always pointing toward where? Toward the center of the circle. Now, the parallel part here of your acceleration, which is responsible for changing your speed. This is what we call tangential acceleration, because it is tangent to the circle, like the velocity. It is tangent, but it could be in the same direction as the velocity or opposite to that. And you know that when we talk about your acceleration, we said it is delta V by delta T. That's your acceleration. Now, the tangential acceleration here, it's tangent to the circle, so it's going to be in different directions here. So what we say here, we say A tan, and A tan here is equivalent to A parallel, which is tangential. Notice that we're not putting an arrow on top of that. We're just looking at the magnitude. And that's why we say it's del dV, the magnitude of V by dt here. Okay? And that's basically what's going to change the magnitude of your velocity, which is basically the speed. So in that case, your acceleration will have these two components. It will have the tangential component, which is the parallel, and it will have the perpendicular component, which is the one which we call centripetal acceleration, which is equal to, in magnitude of it is equal to V squared over R. So the magnitude of your acceleration will be the square root of A rad squared plus A tangential squared, which is A parallel squared plus A perpendicular squared. And of course, if you want to get the angle that the resultant acceleration makes relative to the, let's say, to the center, well, we say tan alpha. Okay, if you consider this angle here as being alpha, okay, it will equal to the A rad over A tangential here. And that will give you the angle that make, and we dealt with it in a previous lecture when we looked at the angle that the tangential, that the parallel acceleration make and the perpendicular acceleration make with the resultant acceleration. So now you can basically perform circular motion, but you will do that with varying speeds as well, where you're going to change both. You're going to change the magnitude of your velocity, and you're going to change the direction of your velocity, and that's why we call it non-uniform circular motion. Let's deal with an example here. A pilot performs a circular dive of radius 800 meters. At the bottom of the dive, which we say here point B, the pilot has a speed of 200 meters per second which at that instant is increasing at a rate of 20 meters per second squared. What is the magnitude and direction of the pilot acceleration at point B? Now, when you're performing circular motion, your acceleration, and as a vector, it has a radial part and it has a tangential part. Now, the radial part is v squared over r, the magnitude of that, which is 200 squared over 800, and it gives you 50 meters per second squared. You have a tangential because they tell you it's increasing at a rate. So you're not going with a constant speed. You're having varying speed, which is 20 meters per second. So the magnitudes of these are 20 and 50, and they are perpendicular to each other. That's why this is here the A parallel, and this is the A perpendicular. They're always perpendicular to each other. And when you take the magnitude, it will be the square root of r rad squared plus A tan squared, which is the square root of 50 squared plus 20 squared, and that will give you 53.9 meters per second squared. So that's now the magnitude of your acceleration. They tell you here has a speed of 200 meters per second. So at this point here, it has a speed of 200 meters, which at this instant is increasing at the rate of 20 meters per second squared. They tell you 20 meters per second squared. That's your tangential acceleration that's increasing at this rate. That's what it means here. And that's why you say that your tangential acceleration here is 20 meters per second squared. Now, you look at this point, that's basically your velocity vector, and that's your acceleration vector, because the acceleration vector will have the tangential part, which is along the direction of the velocity here, and you have the perpendicular part, which is perpendicular to it, and that's your net acceleration here. So the angle alpha, it will be tan of, you're going to put the A rad over A tangential, which will be 50 divided by 20, it will give you 2.5. So you're talking about tan inverse of 2.5, and it will give you an angle of 62.2 degrees. So the angle alpha here, it is the angle between your velocity and your net acceleration. Is this clear? Let's deal with another example. A car slows down at a constant rate. When you look at slows down, when you slow down or you speed up, you need acceleration. Okay. So they tell you it is basically slowing down at a constant rate. That means your acceleration is constant. As it rounds a circular horizontal curve, slowing from 30 meters per second to 10 meters per second. I'm just talking about the tangential here, okay, which is the change in the speed. That it takes to round a curve of 50 meters. What is the acceleration of the car at the instant its speed reaches 10 meters per second? So you can pick any location, by the way. So you look at the circular path that we have here. That's your direction of your velocity. Well, tangent to it or perpendicular to it is the radial acceleration, which is responsible for changing direction. They tell you that you're slowing down. Slowing down, that means your tangential acceleration is opposite your velocity. And of course, this will be your net acceleration here. Now, you want to get your tangential acceleration. Now, you know that V is equal to V0 plus AT. So A will equal to V minus V0 over T, which is equivalent to saying that your A tangential is equal to delta V over delta T. I'm only looking at the change in the I'm only looking at the change in your delta V, and I will look at the magnitude, and the magnitude here will equal to, you're going from 30 to 10. So the final is 10, and the initial is 30, so it's 10 minus 30 over 10 minus 30, which gives you minus 20 over 10, and it will give you minus 2 meters per second squared. That's your tangential acceleration now. Your radial acceleration will be V squared over R, which is 10 squared over 50, and that also going to give you 2 meters per second squared. That's how you write your acceleration in vector form. If you want to get the magnitude, it will be the square root of R rad squared plus A tangential squared. So it's 2 squared plus minus 2 squared. And it will give you square root of 8, and it will give you 2.8 meters per second squared. If you want to get your alpha, the angle that it makes relative to your tangent, which is your velocity, tan alpha will be R rad over R tangential, which is minus 2 over minus 2, which is minus 1. And that basically will give you an angle of minus 45 degrees. And of course, if you want to do that relative to the positive x-axis, and if you can add 180 degrees, and you say it's relative to the positive x-axis, it will be 135 degrees, if you want to use x and y here. So that's basically how you look at uniform circular motion and non-uniform circular motion. So when you're moving around the circle, at any point on the circle, you have radial acceleration, and the radial acceleration is equal to V squared over R. But you take the speed at that point. That will be your radial acceleration. And when you go around a circle non-uniformly, that means varying speeds, right away you know that your A rad, which is equal to V squared over R, is going to change, because V is not the same, it's changing. And you have, at every point, you have to know the speed, and then you calculate the A radial at that speed. And then, of course, you know that you have a tangential acceleration, and of course, your acceleration is a combination of both the tangential and the radial acceleration. Is this clear? We'll try to deal with some questions here. Okay, the first question: you drive a race car around a circular track of radius 100 meters at a constant speed of 100 kilometers per hour. If you then drive the same car around a different circular track of radius 2 100 meters at a constant speed of 2 kilometers per hour, your acceleration will be. And they give you these options. Either it is 8 times, 4 times, twice, the same, half, as great. Well, they're telling you that you're going with constant speed, so you know it's uniform circular motion, and the only acceleration you have is the radial acceleration, which is v squared over r. If you look at the first case, your speed is 100 kilometers per hour and your radius is 100. In the second case, your speed doubles and your radius doubles. Okay. So for example, if I look at A1, which will equal to V1 squared over R1. A2 here will equal to 2V1 because I'm doubling my speed squared over, I'm doubling my radius as well, which is 2R1. And A2 will give you 4V1 squared over 2R1. You can cancel this with that and gives you 2. So basically A2 will equal to 2V1 squared over R, which is twice as great. Is this clear? Now, in question number 2 here, where you really have to make sure where the directions are, point P in the figure indicates the position of an object traveling at a constant speed clockwise around the circle. Which arrow best represents the direction of the acceleration of the object at point P? So it's moving clockwise, meaning this direction here. And they're telling you that the object is traveling at a constant speed. Constant speed, you know, when you go around the circular motion, your A has an A rad plus A tangential, or we can call it A parallel plus A perpendicular. But in the case when you are basically going around with constant speed, this will go to 0 or that will go to 0. And the only thing you have is your radial acceleration, and your radial acceleration always points toward where? Toward the center. So at this point here, your acceleration will be pointing toward the center. So what will be the right answer here? What will be the right answer? D, not A, right? Some of you said A. So you have to be careful, okay? So what we basically did today here, we looked at circular motion. Now we have been dealing with motion in 2 dimensions, which is projectile motion, and we said this is parabolic motion. But also a circular motion, it's a form of 2-dimensional motion. It's always like a plane, okay? But in this case, when you go around the circle, well, there is something that draws you toward the center, and this is when we talked about the radial acceleration. So today we discussed uniform circular motion, and we said you can only do that with constant speed. I said it's wrong to say constant velocity. And we talked about radial acceleration, but remember, we're putting absolute value around that, okay, which is equal to v squared over r. So the magnitude of this is, or we can say here, A rad should equal to v squared over r. Of course, when you go around the circle with constant speed, you have a period which is equal to 2 pi r over v. In non-uniform circular motion, you have the radial acceleration, which is equal to v squared over r, and you have the tangential acceleration, which is equal to dv by dt. Remember, I always said that A is equal to dv by dt. Look here, I'm not using arrows, so I'm only interested in what in the magnitude. Okay. Is this clear? Any questions so far? Any questions? We'll deal more in chapter number 5 when we talk about Newton laws and forces and so on. We'll visit again uniform and non-uniform circular motion when we deal with forces as well. But I want you to understand this now here. Is it clear? Good.